So now let's talk about measures of shape, relative location. How do we use this to figure out if something's an outlier? So some things that we're going to talk about are distribution shape, z-scores, Chebyshev's theorem, empirical rule, and detecting our outliers. So one of the things we need to keep in mind is the measurement of skewness. And so here's our calculation to find skewness, and that can be typically very easily calculated using different statistical software. So here we have an example where we have a distribution where it looks pretty symmetrical. So we would call this a skewness of 0. In this case, our mean and our median are going to be equal. Here we have a moderately skewed to the left. So you notice that the left-hand side of this graph has what we call a longer tail. We have a negative skew value of 0.31. And so usually in this case, the mean is going to be less than our median. Here we have it moderately skewed to the left. Here we go, it's moderately skewed to the right. So the same value, but in a different direction. Our skewness is considered positive, and here we have our right tail that's longer. So in this case, your mean will typically be more than your median value. Here we have a highly skewed data set where we have a skew value of 1.25 with a really long right tail. And so when you have a highly skewed right, you have a very high skew value. Often it's above 1, and in this case, it's very common to see your mean being more than your median value. So if we were to calculate our skewness for our sample apartments, we could just take these values, plug them into the calculation, and we end up with a skewness value of 0.92. And if we graph it, we still see that we have this overall long right-tailed portion of our graph. Kurtosis is concerned with how heavy the tails of the distribution are. So how big of a skew they have using the normal distribution is going to be our reference for comparing our distributions. So if we have a leptokurtic, that means when our k value is greater than 0. Mesokurtic is when our k value is equal to 0. And plekurtic when k is less than 0. So here, the first one we have is leptokurtic, the middle one is mesokurtic, and plekurtic is here on the bottom. So when we're looking at z-scores, we're looking at our standardized values. And so what we're looking at is how far away or how many standard deviations that data point is from the mean. And so when you do that, you're going to take the observation value and subtract it from the mean for that observation and divide it by the number of standard deviations. Notice that this is looking at your number of standard deviations for the sample. When you have, once again, a large z-score, you're going to have a value greater than the mean. That gives you a positive z-score, and if you have a negative z-score, that means your value is less than the mean. So here we have our apartment rents, and we have 70 of them that were randomly sampled. And so we take these values and we calculate the z-scores for our individual values. We see that the z-score for our individual value, our smallest individual value, was calculated by taking 525, which was our lowest value, subtracting it from our average rent value, which was 590.80, and dividing it by our standard deviation for our sample to give us a z-score value of negative 1.20. Chebyshev's theorem says that about 75% of your data values must be within 2 standard deviations of your mean, 89% is within 3 standard deviations, and 94% of your data will be within 4 standard deviations of your mean. So if we wanted to use Chebyshev's theorem with our apartment rent, remember that we have a z value of 1.5 for that lowest value. We have a mean value for my apartment rents of 590.80 and a sample standard deviation of 5.74. So if we remember that we have the rule that at least 1 minus 1 over 1.5 squared must be within that range, that means 56% needs to be between our negative Z value, negative 1.5 and positive 1.5 standard deviations. So that's going to be 509 as my lower bound, and 673 is going to be my upper bound. So in actuality, if we look at this data set, actually 86% of our rent values are going to be in that value. So we're not in violation of Chebyshev's theorem because at least 50% must hit that range. The empirical rule is used to determine the percentage of the data values that must be within a specific number of standard deviations of our mean, looking at a normal distribution. So if we have a normal distribution, then about 68% of our data needs to be within plus or minus 1 standard deviation, 95% within plus or minus 2, and almost 100% plus or minus 3 standard deviations. So oftentimes we use this as a reference to determine if something is an outlier. So it's very common to use plus or minus 3 standard deviations. Sometimes you might use 1.96 depending on what your different rule is for the data that you're looking at. And so here, if we look at our apartment rent here, we have our most extreme z-scores is negative 1.2 and positive 2.27. If we use the criteria that it's got to be outside 3 standard deviations to identify an outlier, based on that assumption, we wouldn't have any outliers in this particular data set.